Okay, so curvilinear and curvilinear coordinates. Okay, so far we've done rectangular coordinates. So when do we need curvilinear coordinates? Well, we need them when we tend to represent the path of the particle in in the coordinate described by the arc length. So S. So this is called the path coordinate. For example, if you can write the equation of the path like that trajectory, then you're best off using curvilinear coordinates. So at any point in the motion of the particle, you can draw a coordinate frame okay, such that this particular vector is in the tangential direction, this is in the normal direction, and this point here is actually the center of a circle at this point. So you can actually, based on the fact that you can draw a tangent, there's an imaginary circle here, okay, and that circle has a corresponding radius. I'll denote that by rho. Okay, and that radius changes with time because when it goes here, it'll be a different size circle, and so on. So the rho is called radius of curvature, and I'll show you how to find the radius of curvature given a curve. Okay, so if it's a circle, then the radius is r. It remains r throughout. If it's a flat plane, if the particle is moving on a flat ground, then the radius is actually infinity, because you can never find the the curvature is going to be perfectly flat, which means that the radius is, you'll never find the radius. It's the center of that circle. It's going to be at infinity. So when we have motion described in this coordinates, we want to know the velocity and acceleration. So velocity vector is given by this coordinate s, the path coordinates, times, well, s dot u of t. Okay. So remember, for rectangular coordinates was something times x, something times y. It's super easy in this coordinate. It's just going to be s dot, provided you know what s is, times u of t. The acceleration can be found by differentiating that expression, and it's a derivation which takes some time. I won't be doing that, but you're free to read the book on how to find the acceleration from the velocity, but it comes from differentiating the velocity. The acceleration in this coordinate frame is given by, there are two components to it. There is a component in the ut direction, and there's a component in the un direction. So what are those components? The tangential component is simply the second derivative of s, which I written down earlier. And the normal component is given by s dot square divided by rho. Okay, you can also write this as v times ut plus v square divided by rho, where v is simply s dot. You could also, well, write this as v times u of t, okay, where v denotes the first derivative of s. So that's formula 1. This is formula 2. Okay. Sometimes what happens is you're given AT and you're told to find S. So there's a formula which relates to 2. ATdV is, sorry, ATds. So if you recollect, there's a formula which goes like this. AT is VdVds. This is something which we covered probably in the first class, right? That is valid for only the tangential component. So what you could do is you can write AT, well, AT is VdVds is the formula. So I'm just going to highlight that. So what you could do with this formula is, if you're given AT, you can find S by integrating this, or if you're given V, or if you're told to find V given AT, then you can also use that formula to find that. Okay, so in this expression here, if you know S, you can find acceleration, but what about rho? How do you find rho? So there's another formula for rho, and it's fairly complicated. You're not expected to remember it. We will give the formula to you in the exam. So for such problems, you will be given a curve. So y equals f of x could be y equals x is the equation of a straight line. Y equals x squared is a parabola. You could also write y equals f of x for a circle and so on. If you're given the curve y equals f of x, then you can find rho as follows. It is 1 plus dy dx square, okay, the whole thing 3 divided by 2 divided by d square y dx square, okay, where this symbol here is the absolute value. What it does is, if you're given any number here, 1, that'll be just 1. If you're given minus 5, it'll become plus 5, and so on. So it basically replaces the value with its positive value, just gets rid of the negative. Okay, any questions? So let's just see how to apply what we've done here on some problems. Okay, so first question. So an automobile is traveling on a curve having a radius of 800 feet. Okay, so the radius is 800 feet. If the acceleration of the automobile is 5 feet per second, okay, you're given the acceleration. Well, you're not doing anything about the tangential or normal acceleration, so it is the magnitude is 5. Determine the constant speed at which the automobile is traveling. So you got to find velocity. And you're also told that it is a constant speed. So let's try to write the formula for acceleration, because we know something about the acceleration in tangential coordinates. So A is ATUT plus ANUN. We have written this down as V times UT plus, sorry, V dot times UT plus V square divided by rho UN. Okay, so the magnitude of acceleration is v dot square plus v square divided by rho square. Okay, so let's see what we know about this. We know the acceleration, it's 5. Uh, we know rho, it's 800. This is an unknown. We don't know v dot. How can we find v dot? Okay, so actually we know v dot. It's 0 because it says constant speed. So this means v dot is 0, but v is not equal to 0. Okay, so you can have a non-zero acceleration with constant speed because there is this term, and this term is, if you from a physics class before, you might have recognized this is the centripetal acceleration, right? It's only due to constant speed. This is 0. So we can say 5 equals 0 square plus velocity is unknown, so I'm going to write this as v squared itself divided by 800. So v equals okay. Any questions on this? Okay, next question. So the automobile has a speed of 80 feet per second at point A. Okay, so given that acceleration of magnitude 10 feet per second square, and you also given the direction of the acceleration. Determine the radius of curvature. So we asked to find the radius of curvature and then the tangential component of the acceleration. Okay. So let's again, we know the acceleration. So let me try to write the formula of acceleration. V dot square plus, well, it is at square plus an square, which is I'll keep that 80 as 80 because I need to find 80, and an is v square divided by rho square. Okay, so I know the acceleration, the magnitude. I do not know the acceleration, the tangential direction. I do not know the velocity. Oh, I do know the velocity. I know the velocity, but I don't know the radius. So if I sub in the value for acceleration and plug in the values, I will have one equation, this equation, and there will be two unknowns: the radius of curvature and the acceleration in the tangential direction. So I cannot solve for two unknowns with one equation. I need to generate one more equation, right? Linear algebra tells you that if you have two equations, two unknowns, you can solve it. So the question is, how can I get the other equation? Seems that I've used the velocity, I've used the acceleration in the formula. Looks like I've used everything, all pieces of information in this problem so far. So how do I solve for? Well, how do I get the second equation? There should be some more information in the problem for me to solve this. What else do you know? Angle, right? So you know something about the direction of acceleration. You know that the acceleration makes 30 degrees with the tangential direction or 60 degrees with the normal direction. So how can I use that? Well, the this is the acceleration. This is the normal acceleration. This is the tangential acceleration. And know this is 30 degrees. Okay, so this is the magnitude of acceleration. Well, this is not the magnitude, but just A. Uh, so can I use that to find something about, can I set up the second equation? There are multiple ways of doing that. One way, well, the straightforward way is the tangential component is going to be the magnitude of the acceleration times cosine of 30 degrees, right? So A cosine of 30. In fact, all these things are actually magnitudes. This is you can also get the normal component if you wanted. It's simply A sine 30. So this is going to be 5 cosine of 30 degrees. Is that 8.66? Oh, it's 10, my bad. 10. So it's 8.66. So I've actually figured out this term. So now going back to should put the units, feet per second square. Okay, so putting 2 in 1 gives 5 equals, sorry, 10 equals 80 or 8.66 square plus velocity square, so it's 80 square divided by rho. So I can solve for rho now because we have one equation and one unknown. It's 1280 feet. Okay, you could actually do it in another way. AN, which is this, is simply magnitude of A sine of 30 degrees. Okay, so that is 10 times sine of 30 is 0.5, so it's 5. But AN is V squared divided by rho, that should be equal to 5. This gives me 80 squared divided by rho is 5, and so rho equals, let's check if this is right, 80 squared divided by 5. It's 128, same thing. Okay, so both ways are fine. This is probably much simpler than the first one. Okay, any questions? Okay, last problem, I'll let you go. Okay, so let's read the question. So a box is sliding along a curved path defined by the parabola. So this is the parabola. The equation of the parabola is y equals 0.4 x squared. When that is, the box is at A, the A is shown there, with coordinates x equals 2 meters, y equals 1.6 meters. The speed is 8 meters per second, and increase in speed, which is v dot, dv dt is v dot, is 4 meters per second square. Determine the magnitude of the acceleration of the box at this instant. So what we want to find is the magnitude. Okay, and so what I like to do is sort of start from the reverse. So try to write a formula for acceleration. It's at square plus an square, which is v dot square plus v square divided by rho square. Okay, so this is the unknown acceleration. V dot is 4 meters per second square right here. Velocity is 8 meters per second. Okay, so the only the two unknowns, there's the acceleration which is unknown, and then there's rho which is unknown. So we need to find either of those. Well, we need to find acceleration, but we can only do it if you are uh, finding rho. So remember, I gave you a formula for rho. This is precisely a question where you can apply the formula. That's because you are given the function, you are given y equals f of x, or the equation representing the curve, which is the parabola. So what I'm going to do is take y equals 0.4 x square, find dy dx, that's 0.8 x, and I want dy dx at a specific point. I want dy by dx at x equals 2 meters and y equals here 2 meters and 1.6. So it's 0.8 times 2, which is 1.6 meters, and d square y dx square is 0.8, and since that's a constant, it doesn't change with the coordinate. Okay, so now rho is 1 plus dy dx square, the whole thing raised to 3 by 2, divided by d square y dx square. So that's 1 plus 1.6 square divided by the magnitude of 0.8. This is a formula which we will give you absolutely. This is in the formula sheet. Okay, so having got that, we can now find the acceleration. It's 4 square plus velocity, so it's 8 square divided by 8.39, which we just found. What I got is 8.63 meters per second square. Okay. Any questions? Yeah.
You solved for load. What did the 3-hash power go?
Oh, thank you.
That's what I was saying.
Yeah, something else. Yeah, that's it. Yeah, my bad. I forgot to write it, but I just copied this from my notes. Okay. Okay, so we're done. So we'll meet on Monday now.